may seem a bit abstract, but that's the general principle. So you need to keep in your mind that the Heisenberg uncertainty principle, the XP, you can't measure the position and the momentum at the same time. That's just one special case, right? The uncertainty principle is very general. I mean, A and B could be any pair of incompatible observables. You can't measure both of them to infinite accuracy simultaneously. They're incompatible in that sense. You measure one, you disturb the other one, and vice versa. Okay? So here's the theorem statement, if you like, and it will take us, let's see, it will take us another 2 squares, 2 half sessions. So the second half here, and the first half of the next session to prove this. So look on this as a theorem statement, and then we'll start the proof. Okay? And the second half of the second session, I suppose you've noticed a pattern. My head goes down. That's because I'm sitting on a little stool. The stool's only about this high, and it's safer than sitting on the edge of the bed, because I nearly fell off once. Not safe. Okay, so we're talking about the variance, the product of 2 variances of observable A and observable B. Okay? So remember, variance is the square of the standard deviation, or sigma, all these terms. Yeah. So the square of the standard deviation. Now in quantum mechanics, the variance, this is the variance of A. It's variance, remember, is the mean, is the average, the mean square deviation. And deviation means the difference between a score and the average score. Okay? Now, and remember this expectation value, or the average, it's a sort of shorthand. I could, I've done it here. Now this is another way this is a kind of shorthand for this. Hold on. Well, I could have. Now remember, your operators in quantum mechanics, the operator that corresponds to an observable, measurable physical quantity, is Hermitian. So I could have put in another vertical line, because this operating on the right, operating on the ket, is just the same as if this were operating on the bra. You could put this here. Okay? So I could have put another bar here, but anyway, I've left it. I've left this operator operating on the ket. Okay. Now, an operator of an observable is Hermitian. Right? We talked about that earlier at length. So I can take one of these. It's the square of. So I can take one of these bracket terms and bring it over to the left side, and I get this. Okay. Now, so we've got something that's the same on the left side as the right side. Now, rewrite that. Just call that alpha alpha. Okay. So I'm defining, it's three lines here. So by definition, I'm defining alpha to be this term here, a hat minus average a hat times psi. Okay, I'm just defining it that way. Now I can do something just the same for observable B, the other one. So A and B. Okay. So just, where I've got A here, just substitute B, and I'll just get just the same thing. Okay? So I'll get, let beta here be this psi. Okay? Alright? Now I can multiply the two the two variances, sigma A squared and sigma B squared. Okay. Now, what is what is sigma A squared? It's bracket of alpha alpha. There it is here, bracket of alpha alpha. And what is the sigma squared of B? Well, it's bracket of beta beta. Right? So, okay. Now you see where we use Schwarz's inequality. Right? Here, we can instead of writing this down, we can say that sigma squared A, sigma squared B is greater or equal to the square of the absolute value of bracket alpha beta. Right? That is Schwarz's inequality that we did the previous session. Okay. All right. Now we start playing. Okay, so we can forget about this. See, we want a generalized Heisenberg uncertainty principle between two, any two incompatible observables, A and B. All right. So we want an inequality. So let's concentrate on this and just forget about this because we want the inequality. Okay. So we now know that sigma squared A times sigma squared B is greater or equal to this term here. So let's start working on this bracket alpha beta. What is that? Well, whatever it is, it's going to be it's the absolute value of, right? So it's going to be a real number. Now inside, in general, be a complex number, complex function, let's say. So we'll let this be z. Yeah. So in the next session you'll see. So this number here, in general, it's a complex number. So let it be z. Letter z. Now z belongs to. Now remember this. We've done this. This is from pure math. It's the big C. It's the set of all complex numbers. This belongs to symbol, I suppose you're familiar with. So this is just saying here that Z belongs to the set of complex numbers, which is a long-winded way of saying that Z is simply a complex number. All right? So you can write it in this form, x plus iy. So Z squared, and in a moment, or next session, we will let bracket alpha beta be Z. Okay? Now, the square of the absolute value of Z as a complex number is just x squared plus y squared. Right? Now x squared, they're both squared, so both positive. X and y are reals, so squared, they're both positive. So common sense just says that x squared plus y squared is greater or equal to y squared. And it's only equal when x is naught. Okay? So square of the modulus of Z is greater or equal to y squared. Right? Now you can rewrite y in y squared in these terms. Can you see where that comes from? Can you see that that is y? Well, just quickly let's do it. So we're trying to solve for y. So z star, so that'll give you x minus iy. So you add those two expressions, z equals x plus iy, and you add that both sides to z star, which is equal to x minus iy. So subtract one from the other, so you'll get 2iy equals z minus z star. So y equals 1 over 2i z minus z star, and then you square the whole thing. Right. Right. Well, we have one more square, one half session still needed to get this result. Right. So I'll just move straight on.